Hi there, and welcome back to the channel. Throughout this series of videos, you will be introduced to topics in optimal control and estimation in a way that you can draw almost complete idea about optimal control and optimal observers. Most of the introduced materials during this journey is borrowed from the book, Applied Optimal Control, Optimization, Estimation, and Control, which is written by Arthur Bryson. This is the 8th part of the series. In this video, I'm going to deal with optimization problems that are subjected to continuous systems with no terminal time constraints and fixed terminal time. Optimal programming problems for continuous systems are problems in the calculus of variations. I highly recommend watching the video in the description about calculus of variations to have some idea about this important subject. Calculus of variations can be considered as limiting cases of optimal programming problems for multistage systems in which the time increment between steps becomes small compared to times of interest. Actually, the reverse procedure is more common today, where continuous systems are approximated by multistage systems for solution on digital computers. Consider the following dynamic: x dot is equal to function f of x of t, u of t, and the time t. This is a nonlinear differential equations in which x of t and u of t are n and m vector functions. Please keep in mind that here we are dealing with functions rather than discrete variables. Now let us consider an index of performance j, which is a scalar function of the following form. The problem here is to find the function u of t that minimizes or maximizes the given function j. As we did in the previous parts of the series, we simply adjoin the dynamic differential equations to the function j through a multiplier lambda of t. The result is given through the function j bar. Let us define the following function h of x, u, lambda, and t. This is a scalar function known as the Hamiltonian function. Please don't forget that lambda of t is our multiplier, which is also a function. We are going to treat this problem a little bit differently from previous parts, where we can integrate by part the last term of the function j bar, which results in the following form. Now we can consider this final form of the function j bar, where we can assume variations in the j bar due to variations in the control vector function u of t for fixed times t sub 0 and t sub f. This variation in j bar can be written as shown. It would be tedious to determine the variations delta x of t produced by a given delta u of t, so we simply can choose the multiplier function lambda of t such that the coefficients of delta x in this function is vanished. Thus, we can assume the following expression for lambda dot. Following the same idea, we can assume the following boundary conditions for lambda at t sub f. Considering the defined function h as shown, we can have an expression for the lambda dot in terms of the functions L as well as f. Now considering the expression of the lambda dot, lambda at tf as well as the delta j bar, we can further simplify the expression of delta j bar as shown. In this final form of delta j bar, lambda of t initial is the gradient of the function j with respect to variations in the initial conditions while holding the function u of t constant and at same time satisfying the given nonlinear dynamic x dot. In addition, the function lambda of t is called the influence function on j variations in x of t since t0 is arbitrary. And partial of h with respect to the function u is called the impulse response function since each component of this partial derivative represents the variation in j due to a unit impulse in the corresponding component of delta u at time t while holding x of t0 constant and satisfying the given dynamic of the process. Now, as we simplify the delta j bar as shown, we can say that for an extremum, the variation in j bar must be 0 for arbitrary given variations in the function u of t. This only can happen if the partial derivative of the defined function h with respect to the control action function u of t is 0. This should be true for all time domain of the process dynamic. In calculus of variations, the following three relations are known as Euler-Lagrange equations. To sum up what we have introduced so far, in finding a control vector function u of t that produces a stationary value of the performance index j, we must solve the following differential equations. First, the dynamic of the process. And second, the expression that we had driven for the lambda dot. The control action function u of t can be determined by setting the partial derivative of the function h with respect to u to 0, or subsequently set the following expression to 0. Keep in mind that we have boundary conditions for the first two terms as followings. At time t sub 0, we have the initial state of the process, and at t sub f or t final, we have the expression for lambda of t sub f given as shown. As we saw in the last part of the series where we dealt with multi-stage system optimal programming problems, here we also are faced with a two-boundary value problem. Before jumping to an example, I think it is good to state the following. As you know, we have assumed the following expression for the h function. Thus, the first integral of the boundary value program exists if both the function L and the dynamic f are not expressed functions of the time t. So for the function h, we can have the following partial derivatives for h dot equals to the partial derivative of h with respect to time t, plus the partial derivative of h with respect to the variable x, plus partial derivative of h with respect to the variable u, and finally plus the partial derivative of h with respect to the lambda. Keep in mind that x dot is our process dynamic given as a function f. Thus, we can rewrite the function h dot as following. And if we go back to our derivation of the optimization problem we dealt with in this video, we also have an expression for lambda dot as shown. By substituting this relation in our shown equation, the last term will be cancelled out, and we left out with the following partial derivatives. So, if both functions L and f are not explicit function of the time t, then the first partial derivative is also cancelled out and we left only with the partial derivative of h with respect to the control action function u. Accordingly, if we let h dot equal to 0, by setting h sub u to 0, we literally saying that h is constant on the optimal trajectory. This is basically what we have driven so far. One last point that needs to be stated here is that for the j function to have a minimum, it requires not only setting the partial derivative of h function with the function u to 0, but also we need to check the second derivative of the function j, which has to be a non-negative definite matrix. As we have gone through the derivation of conditions to find optimal control functions for optimization problems that are subjected to continuous systems, we can now introduce an example to demonstrate what we have shown. Consider a body of constant mass m at rest in a specific initial positions y of 0 as shown by the figure below. P of t is an unconstrained search function of the applied force. The desired task here is to move the mass during t sub f units of time, say 5 seconds, to a terminal position at which t of f is equal to 0. We also require that the final or terminal velocity is 0. During this journey, we need to minimize the shown performance index. To simplify the solution of this problem, we can assume the followings. Let x1 of t be the instantaneous body position y of t. Let u of t be the control variable or acceleration which equals to the force p of t divided by the mass m. And finally, let x2 of t be the instantaneous body velocity y dot of t. The motion of the body can be described by the differential equation p of t equal to the multiplication between the mass m of the body and the acceleration of the y double dot. This is basically the second law of Newton. We can restate this problem as an optimal control problem as following. First, we have boundary conditions as shown below. Second, we have the optimization problem where we have the cost function or the performance index as shown. This objective function is subjected, of course, to the process dynamic. Following the variables we assumed in the previous slide, we can rewrite the dynamic as the mass m multiplied by the control action u of t. We can also further simplify the dynamic by two states x1 dot and x2 dot as shown. Let us put all these information aside and start solving the problem. First, we need to derive the Hamiltonian function as shown by the function h. This function has two terms, which are the L function, which is basically the integrand part of the cross function, and the function f, which is the dynamic of the process. Don't forget that these two functions are joined together with the variable lambda function. Keep in mind the function lambda is two functions, as we have two states x1 and x2 in the process dynamic. By substituting the information from the problem, we can have an expression for the function h as shown. Now we have to state the conditions for the optimality, which are basically the Euler-Lagrange equations as shown below. The first thing that we can notice here is that for the terminal boundary condition of lambda of Tf, we don't have a terminal term in our cross function j. Therefore, we can eliminate this condition. Okay, let us start with the first condition. We can partially differentiate the function h once for x1 and once for x2. The first differentiation gives an expression for lambda.1, while the second differentiation gives an expression for lambda.2 as shown. Secondly, we have to differentiate the function h with respect to the control action function u and equalize it to 0, which adds the following third expression into our set. A set of differential equations has been found from the Euler-Lagrange equations. Beside the set, we can also use the process states. So we have a first set of equations from the process dynamic and the second set of equations from the Euler-Lagrange equations or conditions. No, we need to solve from these sets for a single differential equation. From the first equation, we can have an expression for x.2. We can substitute the second equation into this expression and assign this as equation number 1. From last equation, we can also have an expression for lambda.2. We also can substitute the fourth equation into the expression of lambda.2, which gives a new expression for u dot. Now we can differentiate both sides and have the following relation. We can substitute the third relation into our last expression for u double dot and assign this new expression as equation number 2. Now we can substitute equation 2 into equation 1 and have a single expression in term of the state x1 as shown. This is a fourth-order differential equation that has one variable, which is the state x1. The solution of this differential equation as a function of time is given as following. In order to find the trajectory solution of the state x2, we simply can use the show relation, which is driven from the process state. Thus, the trajectory of x2 can be written as, and most importantly, the function of the control action u of t can also be driven from the shown relation, which is also given by the process dynamic. Therefore, the optimal control law is given as, in all these three trajectories, C1 through C4, K1 through K4, and Q1 through Q4 are constants that need to be determined. To compute these 12 constants, we need to utilize the given boundary conditions in which the terminal time is 5 seconds. So basically you plug in each set of the conditions in the corresponding trajectories. This results in the following matrix, from which we can compute the constant C1 through C4 as shown, and consequently we can find the other constants. The following figure shows the control response or action under which the states of the dynamic respond as shown by the following plot. With the state responses plot, we came to the end of this video. In the next part, I will also go through optimization problems with continuous systems, but when some of the states are specified at fixed terminal time. Thank you for watching, and please do not forget to like the video and subscribe to the channel. See you soon, hopefully.